SpaceX, which is the French agency for space applications and space developments in Toulouse. Well, using Linux in space is a bit difficult, and using everything is a bit difficult because space is a very hostile and complex environment. We need a small footprint. We have radiations, so the system configuration is a bit difficult. You need certifications such as the ECSS. There are specific protocols, specific hardware. The most famous hardware in space right now is a Sparkleon CPU, which is built to be to provide the radiations hardening. There are some specific protocols and hardware such as SpaceWire. So it's not that simple. Nevertheless, the space applications are been using software for a long time. I talked in my previous talk. I talked about the Apollo space flight control, which is based on the IBM OS. And so in the same Apollo program, we have the Apollo guidance computer for the module and for the lunar module. It was very simple for regarding the current technology, because now you can run the AGC on a website in JavaScript, but it was in the 60s. There are specific OS such as RTEMS, VxWorks, or Lightos. Virtualization right now you run most of the time you run the partitions in products such as Xtratom, which is called now XNG by Fensis. We work with Fensis on the project, or another one by Cisco, which is Thales, and which is called PikeOS. There are some real projects such as SpaceX Falcon 9 using Linux on, and they use Linux on a standard x86 system. So that's a bit amazing. Here is a small history of some Linux mission for the space. You can see some, but most of them, they are real missions, but some of them are research missions. But you can see the somewhere. You can see the mission by SpaceX. So what is the satellite system structure? The satellite system is built around the system bus, and there are two parts: the central onboard computer on the left, with the system bus, the subsystem, and the payload. So there are two parts in the satellite. You have the module, the system, embedded system to control the satellite, and then you have the application inside the payload. And of course, there are much more security issues on the controlling the satellite than on the payload, even if the payload should be secure too. For example, if you have a communication satellite, you have the guidance system, and then you have an application to communicate and to send a picture to the Earth or something like that. And most of the time, we will put Linux on the payload's part. And on the ground station, you have a way to command the satellite and to get the telemetry back. The SpaceWire is a very famous base standard for the satellites and for the space missions in general. It was based on FireWire. It was designed by the European Space Agency and the University of Dundee in Scotland. It's a point-to-point network, very high speed, with a low power consumption, and it's used most of the time. It's used with we have a network interface, and then we have a protocol called AirMap to get remote access to registers for any device. And it's based on an IP written in VHDL. You can buy an IP to providers such as Space Dundee. Space Dundee is a university of Dundee. And of course, you need to write driver for the operating system you use. And most of the time there are drivers for RTMS or standard operating system, but it's a bit difficult to get the driver. You have to get to write the driver for Linux. The typical space architecture today is based on hypervisors such as Xtratum, XNG, and you have several partitions depending on the level of security. And of course, you can have a minimum system and Lightos system and RTEM system with a high level of security, and then the Linux system with a lower level of security. So what are the Linux benefits for space applications and Linux benefits in general? There is a support for many architectures. There are lots of a wide community. So the system is not it's not possible to certify the system, but the system is quite secure. It works quite well. There is a support for many communication protocols, and as it's open source, you can add communication drivers and communication protocols such as SpaceWire, even there is no SpaceWire stack today. There are lots of standards, lots of development tools. It's open source licensing. It's quite cheap compared with the current solution for the proprietary systems. You can use, as I said before at the beginning of the day, you can add some real-time capabilities with Preempt-RT or Xenovai. And another very interesting point is a possibility to develop the software on ground and test it on ground, because you can do it on a PC or simple board such as a Raspberry Pi or ARM board, whatever, and then you can test it on the final target, and it's a bit fine to have such a way to work. And of course, there is a huge catalog of Linux software for industry data processing. There are some applications right now for image processing, and you have some components such as OpenCV. Of course, there are some drawbacks. It needs MMU. There was some kernel for MMU-less systems, MMU-less CPU, but it's not fine now to use. It was called Micro-C Linux. So you need at least a 32-bit processor. It was not designed to be a real-time operating system as it's a Unix architecture, and it's quite impossible to qualify the Linux kernel at ECSS level. Another thing is a large footprint and the package dependencies. But of course, if you can optimize the system to get a nice footprint regarding the constraint of the space application. Of course, it won't be the same as an image by RTMS, but it should be fine, nice enough for the space application, and particularly for the payload. So the Linux for Space project was started by the CNES 2 years ago. It was the first project targeted on the Zynq UltraScale Plus based on the Cortex A53 by Xilinx. Xilinx is a very famous architecture in the space industry. And the way the goal of the project was to select a build system, to select the hardware components. Is it preferable to use Yocto or Beeroot, or what is the best real-time extension to use, and finally to run a Linux image, but as a demonstrator on the Zynq, but without running it in hypervisor such as XNG. The current project started last year. Yocto was the right choice because of the BSP availability, and Yocto is an industry standard. We will use Preempt-RT for the RT extension, because as I said before, it's very easy to install and it'll be closer to the mainline kernel. And then now we will run the Linux image both in a native mode or inside an XNG partition. And there was a great work developed by Fentis to be able to run the Linux in a partition. And the final goal of the project is to start an open source community around it to be able to have a standard, a kind of standard of a Linux distribution on Yocto, and to have collaboration and by the industry, collaboration by the academics, collaboration with the agencies or any kind of people interested in the space industry. So what are the Linux for Space steps? The first part, WP1, was the identification of the expectation of the space industry. As a slide, we are not a specialist of the space industry, and lots of industry are not specialists of Linux. And so it was interesting to ask the people what were their experience with Linux. Of course, big companies, some big companies have an experience with Linux and did some real project with it. But for other companies, it was quite new. And for the future of the space industry, it was very important to know what they need to put in the distribution. The WP2 was a definition of the strategy regarding the animation of the community, the creation and the animation of the community, and in order to maintain the distribution in a good level of activity over the long term. And the technical part, the WP3 was to define the layers to build the distribution. First of all, we will try we will target the zinc, and the UltraScale Plus, because it's a very famous architecture, as I said before, in the space industry. But we plan the RISC-V, we plan to use the Raspberry Pi as a demonstrator. And of course, the distribution must not be dependent of one architecture and one BSP, such as the Xilinx one. So some words about the Yocto principles. Yocto is not a distribution. There is a great set of tools and metadata to create a distribution. And the metadata are the recipes, the classes, the config files. They are provided in a layer, which is a kind of directory with a config file. And you get the layer there are layers for the BSP, the layer for the applications, standard applications. And of course, you can develop what you want. You can create your own distro, which is called distribution is called a distro in Yocto. And the distro is a way to define the configuration policy for example, the features such as systemd, OpenGL, using WLARD or not, etc. The check settings for the quality assurance and more parameters. And the image is components you will flash on the board. It's an image depending on the target. For example, for the Raspberry Pi, it will be an image of a micro SD board, micro SD card. But for another system, it will be different. Then you will put the bootloader, the Linux kernel, the root file system, and of course, you can configure additional image features at the build time. At the last in a configuration file, you can add the SSH, X11, debug features, etc. So Poki is a default distro for the Yocto project, and of course that is very famous and very, very well done. Lots of custom distros are based on Poki, and that's I think we will do the same for Linux for Space. So the Linux for Space distro, it was first it will be tested on the Zinc system on chip and on the Raspberry Pi. As Zinc is very famous in the space industry, but the Xilinx BSP is based on a specific distro called PitaLinux. And PitaLinux is a distro, and it's a set of tools to be able to build a Yocto image with the help of some scripts for people, for the people who don't know Yocto actually. It's quite an issue for us because the Linux for Space project must not be dependent from PitaLinux. We use PitaLinux as a previous project because it was the default configuration, but now we have to build a distro we can use on any kind of Yocto BSP. But of course, the Linux for Space distro will be based on Poki. Some words about the space features and the constraints. Most of the time, we got some information from Greek people from the CNES about it. We didn't know actually because we are not specialists of the space. And most of the time, everything, the system is loaded in RAM. We don't use any file system. For the root file system, it's not possible right now. It's not possible to use a standard file system such as X4 or anything like that. And the RAM is quite short if we compare with the system today, or even with a standard mobile phone. We need and inside the small RAM, we have to put the hypervisor. You have to put the partitions with all the OS and the applications, as I showed in the slide regarding Xtratum and the hypervisor. So if you want to be compliant with these features, we should use an initramfs, which is a way to run the Linux system in RAM. For the first version, we should provide a SpaceWire and AirMap support, but there is, as I said before, there is no SpaceWire stack available for Linux. So there is a free IP designed by the IRAP in Toulouse. We can get the IP, and the IP is very famous at the CNES because they are close to the IRAP, and they did some job on the development on these IP. So of course we have to develop the driver for Linux, driver for the IP, and there is a simpler way to test a kind of SpaceWire simulation on a board without an IP, with a SpaceWire AirMap library, which is based on TCP and was designed by the Japanese engineer some years ago. But according to some contacts in the space industry, this library is fine and is used for test purpose in the space industry, even in France. Okay, so I can show you a small demonstration of the beginning of the project. So I will stop the sharing, and I will share my whole screen. Okay. So I will show you how to configure a simple Yocto application. So if I go to Yocto, for example, on a Denfert distribution, which is a LTS, which should be fine for space application, it's long-term support version of Yocto. So I have an example of Raspberry Pi on the Raspberry Pi, and everything is designed in the configuration file. Sorry, it's already open. So I can show you the configuration. For example, for a small configuration, the target is a Raspberry Pi 3, and I use a Linux for Space distribution. And the distribution is defined in a layer, and the layer is here. So I can show the architecture of the layer. So the layer is very simple right now, but it's designed as a definition of the layer here. A very simple application running at the beginning of starting the system, which is just a simple message, and a dedicated image to build the application, to build the image, actually, to build the image to flash on the board. But now it's on a Raspberry Pi. So if I open the definition of the distribution conf by throw Linux for Space from conf, you can show it's based on POCI. We just define the name of the distribution and the message we display at the beginning, and then I can show the image, recipe score image, and this is an example of the basic image we can start. So it's based on the core image minimal, which is basic image from Yocto, and I just install my application, and my application is a simple script running on the board. Now I can show you the simple script. The simple script is something like that. Hello space.sh. So it starts at the beginning when booting the board, and now we have a program running in a loop. Okay. So once I build the system, I can show you the system running. So I will stop the system and restart it on my Raspberry Pi. And there is a characteristic of this system is a way to it runs in an initramfs. So it's very simple to do that in a Raspberry Pi thanks to the configuration file. So you have a Hello Space application starting. You can stop the application because it will be to see the configuration. So if you mount the partition on a boot directory, you will see the configuration of the system. So there is the kernel, there is a RAMFS containing the distribution. So you can notice it's about 2.5 megabytes if you compress the system. So it's very short. And if you open the configuration of the board, the Raspberry Pi, you just need to have this kind of kernel configuration, and then on the config file, you just have to say you run the system from an initramfs. Okay. So it's quite simple. It's the WP3 just started some weeks ago, so we have quite nothing to show regarding the specific support, including the SpaceWire. But we trust it's a very interesting project. We have great partners such as Fentis, and in the near future we will test our developments in the Fentis hypervisor. So if you have any question, yes, I can bundle the initramfs in the kernel image, but for me in the Raspberry Pi it was better to do it in this way. So the hypervisor is XNG by Fentis. You can take a look at Fentis website. They are great people, very good in technical stuff. So this is it's this hypervisor. Xtratom was at the beginning. Xtratom was an academic project at the University of Valence in Spain, and then Fentis was created on the project. It was at the first time it was a full open source project, but right now it's an industrial project with the support of ARM systems by Xilinx or any kind of I don't know what is the hypervisor footprint. I don't know really because I'm not from Fentis, but it should be very short. It should be very short. Of course, you can run any kind of hypervisor, but Fentis XNG is a reference in the space industry. Do you have any question? Today is quite not possible to follow the project, but we will start wiki and a website at the end of June, because we are currently developing the application, the distribution, sorry. And as soon as we have a kind of support from the SpaceWire, for the SpaceWire on the Zibo board, which is based on the Zinc, or any kind of emulation for the Raspberry Pi, we will provide the sources on GitHub to start to have interest from the space community and the space industry. So, do you have any other question about Yocto, about the project, about any subject you want in the? So, just another information, additional information. There are some there are some similar projects, such as AGL. AGL is an automotive project, is based on Yocto. And so, no, it's not AGL, automotive grade Linux, not QNX. QNX is proprietary. So if you check out the website of AGL, they will have a similar approach because they develop on Yocto, but of course it's a very big project because the market of automotive is much bigger than the market of satellites. In last year, there were about 1,700 satellites, but most of them were sent by SpaceX for their space internet Starlink internet project. And so, as I saw on the statistics, there are around 80 million of vehicles sold by year in the world. So it's absolutely different. But automotive Linux, AGL is famous in Japan. It's still used by Toyota, and we hope it will be the case for our project in the near future, to be used by the agencies around the world, to be used first in Europe by the ESA, the CNES, of course, the industrials, and maybe in the near future in the world. Okay. No question. So thank you for attending, and see you in my last conference this afternoon. About it will be about Android Automotive OS at 4 p.m. Thanks a lot, and bye.